Uh,
Recording.
okay. Good morning, good afternoon, everyone. It's my great pleasure to introduce our distinguished speaker, Professor Panagiotis Souganidis. Professor Souganidis is a renowned mathematician, currently serving as the Charles H. Swifting Distinguished Service Professor in Mathematics at the University of Chicago. He is internationally recognized for his groundbreaking research in partial differential equations, stochastic analysis, and applied mathematics. Today, he will be sharing insights about optimal control of Dyson equation and large deviation for random Hermitian matrices. Please join me in welcome Professor Panagiotis Souganidis.
Thank you very much. Thank you for your introduction and also for the invitation to speak at your conference. What I want to talk is work that is almost complete with Charles Bertuzzi and Pierre-Louis Lyons. And as the title indicates, I need to touch upon all these topics. So let me begin with the plan of the talk. I want to talk a little bit about random matrices. Just encyclopedical knowledge. Then I want to talk about the control Dyson equation, which leads to a PDE in infinite dimensions. Then I want to say a few things about this equation. This is a Hamilton-Jacobi equation in the space of measures. And I want to conclude with a discussion about the large deviations for the spectral measure of symmetric matrices. And there I want to bring up this very famous formula in mathematical physics, the Harris-Chandra-Itchison-Zuber formula, and then to characterize the rate for the large deviation. Okay, so let me start with each one of these topics. I have prepared too much material for 40 minutes, so we'll see how it goes. So random matrices, it's by itself a whole subject. It's a huge topic. And random matrices, turns out, they play a very important role in quantum mechanics, in free probability, statistics, combinatorics, quantum field theory, telecommunication models, etc. And just to put things under perspective, I want to discuss a couple of these applications. So one is the large random matrices and statistics that were introduced in 1928 by Wishart. And this was actually the way the random matrices were created. So Wishart's problem is you have a matrix with n dimension n and m. It's a data matrix. The columns represent observations of a vector in Cm. And the entries are IID random variables, and there is a covariance matrix, sigma ij, which is the expectation of xi, xj. And the goal of Wishart and the problem in statistics is to find the effective dimension of the system, which means it's the smallest dimension with which one can encode all the variations of the data. And the analysis of that in statistics is based on the study of the eigenvalues and eigenvectors of this covariance matrix, which is x times x transport, and to estimate the covariance matrix of the average by observations on the matrix X. So it's a simple looking problem. And indeed, if m is less than n, remember m is the dimension of the space, n is the number of observations. The problem is simple because it's nothing else than the law of large numbers. You can approximate by the law of large numbers the expectation of these quantities by the weighted sum. And the conclusion in this case is that variations of the data take many space in the eigenspace corresponding to the few large eigenvalues of the matrix X. Things become more complicated when when the space where they make the observations and the number of observations is comparable. That means that either the number of observations is rather small or the dimension of the observation is very large. In this case, when m is about n, then you cannot use anymore the law of large numbers. This matrix here, the sigma hat, is not a good estimator. the spectrum of the eigenvalues may be more continuous, and study the local properties of the spectrum becomes the real issue. In quantum mechanics, you can guess there are two names associated with that, Wigner and Dyson, who said that, okay, one way to understand highly excited nuclei is to assume that the eigenvalues are random and try to get conclusions from there. So again, the spectral distribution of the random matrices becomes an issue, becomes an important problem. And let me conclude with quantum field theory, a topic I know very little, but it brings in some of the formulas that will come up later on. So an important quantity to understand in quantum field theory is this variable here, Zn. This is the expectation of the exponential of a trace of the polynomial of matrices. And the idea is to understand what happens as n goes to infinity to this quantity. And the reason this is important is that if you can get an expansion in terms of n, then that expansion of the logarithm identifies certain important maps for the theory. As I said, I know nothing more about it, but as you're going to see later on in the talk, this quantity Zn is going to show up. Okay, with this very brief and perhaps a little bit incoherent introduction to random matrices, let me continue now with the concrete parts of the talk, and one is the Dyson equation. So the Dyson equation plays a very important role in mathematics and physics, especially in statistical physics and the study of quantum chaotic systems. And let me explain without being very technical at the beginning what it is. You have a matrix valued ODE, A dot n equals dnt, where dn is a Hermitian random matrix. And what one tries to understand is the behavior of that ODE as n goes to infinity. Now, why random matrix? Where is the randomness come in? The classical examples of this driving force, which is the dn matrix here, two classical examples is, one is each entry is the sum of two independent Brownian motions with the appropriate scaling, or it can be a two-dimensional Brownian motion, wij, for each point. And again, everything is, first of all, it has to be symmetric. So wij has to be equal to wji. And all the Brownian motions are independent. So that's the Dyson equation at the simplest level of the written as a matrix. Now, another way to see that is when people talk about the n-dimensional Dyson Brownian motion, they're talking about the stochastic particle system. So lambda n here is a n vector of these components, which interact with the repulsive logarithmic Coulomb potential. So this is all these things, all these big words mean that the lambda, each component of the particle system evolves with this stochastic differential equation, where it's a scale Brownian motion here that we saw before. And this is the sum, this is the interaction, is the sum of one over the difference between the different components. And from here, you see that it's repulsive because this can go to zero, and if the eigenvalues come close to each other, and therefore the stochastic DE may not make sense. So since we are dealing with Hermitian matrices, we might as well order the eigenvalues are real, although the matrices may be complex. They are ordered. So I will be working with this space, which is the first quadrant in Rn. So there is this order among the elements. Wn here for this stochastic D is d-dimensional Brownian motion. And the coefficient beta here, right now, I will write and not write later in the talk. I'll forget it in some places to simplify things. Depends on the kind of matrix you used before, the Dn matrix we talked. So it's 1 when the Dn is this simple sum. It's 2 if it is like that. And don't ask me why it is like that. But it plays an important role. And the role is the following. if beta is between 0 and 2, and you start with an initial value of the eigenvalues in that space sigma n, then the lambda n's stay there. That means there is no collisions effectively, and the stochastic D has an almost sure global solution. That's a deep theorem in probability. While if beta is bigger than 2, you may have collisions, and therefore the stochastic D is not well defined. So later on, we're not going to see it it shows in our work, but not in the lecture, this dichotomy here. The 2 plays an important role. So that's the Dyson model. And anytime you have n variables in physics, in statistical physics, it's natural to look at the mean field limit, at what happens as n goes to infinity. And this is actually things that Pierre mentioned earlier somehow in terms of statistical feelings. So it's important to understand, or interesting to understand, the mean field limit of the Dyson-Brownian motion. So I rewrote here the stochastic D. When you look at the mean field limit, you take this strange-looking empirical measure, which is 1 over n, the sum of the Dirac masses at every component. And it turns out that as n goes to infinity, the MNs converge weakly as continuous functions to the space of probability measures, almost surely. And the limit density here, M, solves this equation that looks very simple and it's also difficult, is the so-called Dyson equation. H of M is the Hilbert transform of the measure M, and M0, of course, is the limit of the empirical distribution at time t equals 0. There's a long history behind this problem. There are 2 ways of proving it. You get either weak solutions in that space in C of P, and this is work by Chan, Rogers, and Shi, and others, or you look at, you pass to the limit in the integrand you integrate this empirical measure, and that's recent work of Bertuzzi, Depay, Lasry, and Lyons. I'm not going to talk more about how either of these approaches. The only thing I want to do here is explain why one gets this equation. And I think this is motivating, because if you have not seen this before, you may not see how it's possible to go from this stochastic D here to such an equation. So let me write here a caricature of the proof. You don't have to follow all the details, but basically you want to find a weak limit. So what you want to understand is the evolution of integrals of smooth functions against this empirical measure. And what I did here, I wrote such an integral, and I used Ito's formula to figure out what its evolution is. So you do obvious things. You do Ito's calculation, and you get 3 terms. These are 2 terms here, because there are 2 terms there, and a half of the correction we get from Ito's integration, which I call it here 3n. So let's look at each one of these terms quickly. So the IN, as I said, is 2 terms. The one is C is this, the deterministic part of C is the drift of the stochastic D. And if you observe a little bit what it is, this is the sum of that sum. So if you write it, this term here can be thought as a discrete version of the Hilbert transform. And so if you let n go to infinity, and you know there is a weak limit and so on, this complicated IN converges to that term, which is the one that gives you the drift in the Dyson equation. And it turns out the other 2 terms go to 0. For example, the second term in this sum here, which comes from the Brownian motion, goes to 0 almost surely. This is the role of the additional n we have here. So it goes to 0 almost surely because it has mean 0, and its covariance goes to 0. And the third term is the easiest thing, the deterministic part up here, the third term, because again, this extra 1 over n says that this goes to 0. So that's how the Dyson, that's a caricature of the proof of the derivation of the Dyson equation. One needs to work about all these things, but that's how you should think it comes up. Okay, so what is the forced Dyson equation? The force Dyson equation is you just add a forcing term on the stochastic the system or the particle system. Here, the alpha I is some control that you impose in the problem, and then you repeat everything I said before. And in this case, what you do is you get a control Dyson equation, which is the Dyson equation before, plus this additional forcing term alpha. You may say that we didn't have anything else to do, and we put that alpha there to complete the theory. But you're going to see later on that this is motivated by large deviations, and in particular, moreover, one can put even more general functions of alpha. So let me now talk about the control of the forced Dyson equation. So control theory means you have some dynamics and you have a payoff, and you try to optimize that payoff. So the dynamics here, so this is an infinite dimensional now problem. The dynamics are this control Dyson equation. So alpha is a control. The admissible controls are pairs of solutions and controls that you can you solve that equation. So we are not very careful here about what are the exact conditions of alpha and m, but we assume that this set is non-empty, and it is non-empty because, for example, if you take alpha 0, it's the previous Dyson equation I talked about. The payoff, it's this double integral. So you're integrating something here, which is like it will be, if we will finite dimension of the kinetic energy, and we put some forcing term, and there's some terminal condition. So this is the payoff, this double integral with the forcing and the U0. And the goal is to understand the value of the optimization problem, which is to minimize this payoff over all possible controls. So what happens once you do that, then, and the word Bellman has come up several times in these first two lectures, you expect that this value function, which is now, its variable is a measure, the measure that was up here, it should solve some kind of Hamilton-Jacobi-Bellman equation. And indeed, as we prove, and we will discuss that later on, it turns out that this is the unique continuous solution to this Hamilton-Jacobi equation, which is set on the space P2 times omega t. P2 is the set of probability measures with finite second moments. Okay, so another way to write this PDE, if you have not seen it before, is these two brackets become the integral over m of the m derivative of u. The next transparency will explain the meaning of all these things. And this one is just the integration by parts. You put that there, and you can write like that. Okay, so since I will be talking about these derivatives, let me describe them a little bit. So what is the meaning of these derivatives? The partial mu is nothing else than the classical Gateau derivative. So we do what we learn in functional analysis. We make this finite difference, we pass to the limit, and if there is a density here, that's the Gateau derivative. And when I use the d, the capital D m with subscript m, it's the derivative of u along vector fields. So I wrote here the definition because this terminology may mean nothing to most of us. So we perturb now, instead of, we are giving a measure m, and what we are doing is we are moving it along, this is the push forward with a perturbation of by a vector field phi. And if you formally write down what that means, that's what is going to give you the m derivative. Sometimes this is the intrinsic derivative, some people call it a Lyon's derivative. And you see from these two formulas that the dm is this y derivative of capital Um at y. Y is the variable that the Gateau derivative is going to have. And it's a confusing thing, I would say, because this looks like it's two derivatives, but it's really a first derivative. It's a first derivative with respect to measure. With this in mind, where this bracket here was nothing else but the soup on the transport along any vector field beta with the energy as mentioned here. And make the analogy with finite dimensions. This will be like the actual derivative. It will be the square of the actual derivative, which is the soup of, if it is p here, this is minus pw beta minus a half beta square. So that's the analog in finite dimensions of this quantity. So that's the PDE that comes up. So going forward. All right, so there is a more complicated, more difficult version of this control problem, which is the target problem. The target problem, the dynamics are not only you assign the initial data mu, but you also assign the terminal data mu. So you are trying to control this Dyson equation to reach from one measure, go from a measure mu to a measure nu. The admissible controls then will be the set of m's and alphas that have this property. One can prove it's non-trivial. And then when you write down the payoff, there is no u0 anymore. The variable now is the nu. And the value function will be a function that depends on mu and nu. And it is the infimum of that quantity as before. And it turns out that this is, again, a unique solution to some equation. But now the initial condition is a strange initial condition. It's this, we'll call it a characteristic. It's like the fundamental solution of the problem. It's a function that is zero if the measures mu and nu are the same, and it's plus infinity otherwise. If you're more familiar with finite dimensions Hamilton-Jacobi equations, and you forget this drift term here, and you just look at ut plus a half ux squared, this is like x minus y squared over 2t. And y plays the role of mu, and mu is the x. If there is no Hilbert transform, and if there is no forcing, this equation here is nothing else but the target problem in the classical Benamou-Brenier variational setting for mass transport. Okay. All these things may be new to you, may be completely confusing. Now, let me try to unmask some of the difficulties that the real mathematical difficulties, because things are not as simple as I'm writing them down. And to understand that, you have to bear with me for 5 minutes on a transparency that in a slide that looks technical, but will explain the difficulty of the problem. So instead of writing, let's say we reformulate the dynamics. Instead of writing ds of m plus dx of hm plus alpha, we put these two together. We call them beta. And now this is the control. These are their dynamics. We have beta, and this everything is 1D. So there's a coefficient beta, and we solve this transport equation. It looks much simpler. Parenthesis, before I do that, associated with the Dyson equation is what is known as the free entropy. So it's a function, it's I don't have time to explain more what it is. It's this double integral of the logarithm of mx and my. And this quantity has, and again, I apologize for its technical transparency, but there's no way I can explain to you the difficulty unless I use some terms. The m derivative of that quantity is nothing else but the logarithm. This is a linear function in m, so bilinear in this way. So when you take one derivative, you're going to kill one of the m's. So that's the m derivative. And the intrinsic derivative of that is nothing else but minus the Hilbert transform. So the connection between this entropy and the Hilbert transform is that the intrinsic derivative of the entropy is minus the Hilbert transform. So keep that in mind. So, and moreover, if I evolve the entropy with this transport equation, we get this identity. So now I set up all the technical terms, and I can explain the difficulty on the control problem. So I summarized everything up here. So the whole idea, as I said, is to take the Dyson dynamics and change the m alpha square term here by using the beta. So alpha becomes now beta minus hm. You go in, you compute. I said that it's a simpler formula, and at the beginning it looks much more complicated because we went from a pure m alpha squared quadratic to something that has all these terms. And then magic happens. There is famous or not identity in complex analysis, which is called a Kotler's identity, which says exactly the following, that if you integrate the square of the Hilbert transform times m dx, you get a constant, which turns out to be pi squared over 3, times the integral of m to the cube. So basically, the integral against the measure m of the square of the Hilbert transform of m is nothing else but the L3 norm to the third power of m. So with this in mind, we come up here and using the property, the transport we know for the free entropy, we can rewrite the functional as something simpler, where now here we have a half beta square m, no alpha anymore. But now, on the other hand, there is this additional term, which is the m cube. And the rest of the stuff, you can think of them as going out because of the integration. So one could decide to look at this evolution. I shouldn't have put this becomes a terminal condition. So the terminal condition here is like u0 mt minus the entropy of mt. And you try to decide to control this problem, where now the dynamics are simpler, and you have to deal with this m cube. So inside this problem, although it doesn't appear at the first formulation, there is this property that you can only do it, you can only make sense of this payoff if you have measures which have finite L3 norm. So that's a condition, and it is hidden in the problem. And that's what makes the problem interesting. So you know now all the difficulties. Let me move on and explain a little bit the Hamilton-Jacobi equation. This was the equation I stated down at the beginning. The word viscosity solutions has come up already in 2 lectures so far. We know there are no global smooth solutions to this problem, and that's one difficulty. So one needs to have a notion of weak solution. We are in infinite dimensional space, so this is in P2. The variable is a measure, it's not in Rn. And due to the singular form that I explained, anytime we evaluate this equation, and since we're going to talk about viscosity solutions, we're going to evaluate it at maxima or minima of differences like u minus phi, the maximum point or the minimum point has to be in L3. And to do that, we need to modify the choice of test functions and then solve difficulties that come with that. So let me touch upon that. So typically, the notion of viscosity solution had u minus phi. Here, we are perturbing the test function phi by a small multiple of the free entropy at m. And that's when we look at the maximum. So we are assuming that we have a, let's say, a strict global maximum of this quantity now, phi is given. And then what I do here is I redo the calculations I did earlier with the controls, but I redo them using the function, this particular combination here. I'm not going to bother you with all these, tedious to go through them. On the other hand, it's very simple. There is nothing more than expanding that square and computing all the terms. But the only thing I want to point out is by expanding the square, we created this term hm0 square m0. This is where Kotler's identity comes in. And also, when you look at the transport of the derivative of the entropy, you also create another term that comes in the Kotler's identity. So having said all that, after all these modifications, you get this equation. So the definition of the solution is that if u minus phi minus delta em has a maximum, you have this identity, which tells you this inequality, which tells you what? There is this term here that is strictly positive. And so the claim is that at the moment you put in a notion of solution, of viscosity solution, because of Kotler identities, the maximum point automatically will be in L3, and you have an upper bound on the L3 norm by derivatives of the metric of the phi there. This may look like a trick. It's a classical fact in the theory of viscosity solutions. If there are singularities in the problem, you adjust the test functions to take care of these singularities. And here the adjustment is through the EM, but on the other hand, now it creates an additional problem. You have to create elements in a different space in L3. Okay, and then of course one can define a notion of viscosity super solution by adding this delta EM there, and then you get the opposite inequality. And again, you see there is a term that forces the local minimum to be in L3. And the theorem we have is that if you have an upper semi-continuous subsolution and a lower semi-continuous super solution, if they are ordered initially, then they are ordered for all times. Just to make a connection with discussions, what you had earlier in the talk of PLE, this is not a case that there are no global weak solutions. We are dealing with this. This is a version of what is known in the community as mean field game of control. So we don't have this system that you saw in the previous lectures. We have a scalar equation, and it has a variational formula, so it makes sense to look at it globally. What we are proving here is there's a comparison principle. Okay, so let's sketch the proof of that. This is it. Basically, if you are familiar with the notion of viscosity solutions, you double variables. Here, the variables are measures. You substitute the x minus y square over 2 epsilon in finite dimensions by the 2 Wasserstein metric between the square of the 2 Wasserstein metric between the m and m prime. And you have to penalize a little bit time. And since we are doing some kind of a maximum principle type of proof, you have to subtract some multiple of time. It's classical. Let's not worry. This term is like little o of 1, and this is like little o of 1. We take out of the way. Our definition says that the m and m0 are in L3, and because of m0 and m0 prime are in L3, because of that, they don't have atoms, and because they don't have atoms, the square of the Wasserstein distance is differentiable at that point m0, m0 prime, and the m derivative with respect to m0 is the same as the m prime derivative with respect to the thing. So we have this property. And we have this monotonicity, which is a result of the monotonicity of the Dyson equation that I'm not touching here at all. So if you use all these conditions, you put them in, and you find that a contradiction if this quantity had the positive maximum. And so we prove the comparison principle, except one point. To make this proof work, you don't only need the W22 to be differentiable at the maximum, you want it to be have some kind of differentiability in a neighborhood of m0, m0 prime. So that takes a few pages or another paper to resolve that. Actually, you have the case. What is the difficulty? Once again, the square of the Wasserstein distance, of the 2 Wasserstein distance, is not a smooth function in general. As I said, if there are atoms, it's not differentiable. And so in a neighborhood of the point m0, m0 prime, you cannot claim that it's a C1 function. It's not like x minus y squared. So to build these points here, you need to use the fact that although it's not differentiable, is semi-convex. And because of that and some sophisticated arguments, you can obtain what you need in order to make the proof work. So that's a hard work to get this comparison. Okay, let me talk now about the target problem. The target problem, as I said, as you may remember, has singular initial condition, this function in, which is 0 plus infinity. And if we assume that is, we are at a point that has finite entropy, then we can prove there exists a unique solution provided among the class of functions which are, let's say, non-negative or bounded below by Ct. When you evaluate the u at mu n and at the same variable here, that goes to 0. And otherwise, it goes to plus infinity if mu and n are, and nu are positive distance in the Wasserstein set from each other. Always think finite dimensions here. The analogous result, if we didn't have the Hilbert transform here, and we were in finite dimensions, this will be a ut plus a half du square. Then the fundamental, this solution here would be like x minus y squared over 2t. And these two properties, of course, are correct there. So when this is finite, this is there's a unique solution. In the last transparency, if I ever reach there, I will tell you what happens when this is infinite. Okay, so let's go now to large deviations. So large deviations is a whole field in probability, and there are three pairs of actually there are 5 names associated with that in pairs. So it goes back to Kramer. Then, of course, there is Donsken and Varadin, and there is Wenzel and Friedlin who redo what Donsken and Varadin does, but for diffusion processes where things are simpler. Let me explain here very briefly the Wenzel-Friedlin theory, touch upon it. So what is large deviations for diffusion processes? You start with what is large deviations? To understand, to study events that have very small probability and to figure out how small that probability is, and it turns out to be exponentially small. That's large deviations. So if you study, let's say, an ODE, vxt equals x dot equals bxt dt, then one way to do that is you perturb by a small Brownian motion, and you want to see what happens as epsilon goes to 0. And if the trajectory, okay, so there may be some difficulties there. So the statement, the large deviation statement for that is that if u is some subset of the space of trajectories, then you look at what is the probability that the terminal condition here, x epsilon capital T, is in that set U, then this is necessarily if the xt here, this is the x epsilons go to x. If you choose a measure, a set U here, such that does not contain the the deterministic solution at time like t, this probability will be going to 0, and is going with, since I put an epsilon here, like an epsilon square, and large deviation says that epsilon square logarithm of that is, this is the rate. This is the rate of large deviations. Okay. It turns out that you can express this in terms of PDEs by writing down here the equation satisfied by the probability that x epsilon belongs to some set A. In this particular case, this solves this simple linear second-order differential equation with initial condition, the characteristic of the set A. And if we perform this here, this should be an epsilon square. If we perform the change of variables, you get this equation here. Now, we claim this is a nice equation. The average person sees that and says, I don't see how this is a nice equation because we went from something linear to something non-linear. But nevertheless, one can prove here that the V epsilons have a limit and they converge to a solution to this problem, and which is given variationally by the formula that I stated earlier. So this is one way to find the rate function in large deviations without invoking either the Donsken-Varadin theory, which is like using a nuclear bomb to solve this problem, or Wenzel-Friedlin that requires a fair amount of probability. So that's a way to do that. I'm going to skip this if there's no time. There's a difficulty when t equals 0. What happens at t equals 0? Because remember, we may have this target problem. but let's avoid that for now. And let's go now to Hermitian matrices. I'm running, I think I have 3 minutes to finish this. So at least let me tell quickly what happens. So when you study large deviations, you want to start the spectral measure. An important quantity to study, and no time to explain that, is this very complicated looking thing, which is you take the exponential, the beta is the old beta, minus n/2, the trace of the square of the matrix AN minus U, BN, U transport, d mu n. So A and beta here are Hermitian matrices. U is a unitary orthogonal matrix in Rn, and mu n is the Haar measure on the space of orthogonal matrices. So this is, you look at that and say, okay, this is getting now out of control. Guionen, Zeitouni, making some assumptions on the empirical distributions of the original eigenvalues and using Dawkins-Varadhan theory, were able to prove large deviations for that. What we wanted to do, and now this was our motivation to look at this problem, was to understand a formal argument by Matichin. Matichin is a mathematical physicist, is not a mathematician, which is based on what I advertised at the beginning on this Harishchandra Itchison-Zuber formula. Okay, if this is complicated, now you look at that and you say, okay, how this thing came up. This is the determinant of the matrix whose elements are the exponential of minus n/2 of xi minus yj. X here are the eigenvalues of the matrix An, and y are the eigenvalues of the matrix Bn. The script D's are the Vandermonde products of these eigenmatrices. The Cn is some constant. And how do you come up with this? Actually, this that looks so complicated is you can read the Itchison-Zuber paper. It's a paper in math physics, so it's addressed to physicists. But basically, you get this formula by doing some computation in the fundamental solution of the heat equation on the space of Hermitian matrices. So I think that's enough to explain that. So the idea of Matichin was to take this problem here, use this formula, and put some time in it. And so you see I put a time here. Again, this has to do because of the way it was derived through the heat equation. And then you compute the equation that this IN solves. Now it's a function of x and y. And it turns out it solves this equation here with a transport term, which is I wrote it as Hn because think of it as a discrete. I know I'm running out. I want more transparency and I will finish. It's like a discrete version of the Hilbert transform. And of course, large deviation means to understand the limit of that as n goes to infinity. The epsilon that I had earlier has become here, it's 1/n. So that's why the 1/n squared. And I go through the program I described. So this is you do an exponential change of variables. And then one has to pass to the mean field limit on the equation as n goes to infinity, and obtain at the end the same Hamilton-Jacobi equation that I proved earlier. Now, this is again 1/3 of the paper, so it cannot be done this way. So I think I just go to this, to go the last thing, which is what is the characterization of a solution to the problem when the initial measure has infinite entropy. And it turns out that in that case, if you try to study the large deviations don't require you to have finite entropy initially. And then what happens is when you have infinite entropy initially, the limit of that quantity has to be capital N there, is nothing else by looking at nearby points, measures nearby nu, subtract there, which have finite entropy, you subtract it from there, and then one can prove that this has a limit. And this is the characterization, the complete characterization for large deviations, even in the case where the target measure has infinite entropy. I'm sorry for going so fast at the end. I'll be happy to answer any questions that you may have. And I had forgotten to turn on my camera or the video this time. Okay, so that's it, and
Okay.
I'll be happy to answer any questions. I put too much stuff, and it becomes complicated. Okay, thank you very much.
Okay, thank you very much, Professor Souganidis. So now we open the turn for comment, questions. So please, if anyone has a question, just do it. Someone type in there. Okay, so if not, let us thanks Professor Panagiotis for
Thank you very
his
much.
talk. Thank you very much, Professor. So now I give the word to Anna.
Okay, thank you, Diego.